This will be the third and final part of our quick stop to talk about spectroscopy. In this one, we're going to look at electronic spectroscopy. We'll look less closely or in less detail at electronic spectra, mainly because we don't have as good of a universal model to describe electronic spectroscopy as we do for, say, vibrational spectroscopy, where we have the harmonic oscillator, right? When I say electronic spectroscopy, first of all, realize we're talking about transitions that would occur in the ultraviolet or visible part of the spectrum. So we're at higher photon energies than what we've been talking about in the last couple of segments. When I make an electronic transition, what's actually happening is we're promoting an electron from one molecular orbital to another, right? So assuming our molecule starts off in the ground state, we're taking an electron from one of the orbitals that's normally occupied and moving it to an unoccupied molecular orbital. Again, the energies associated with this should correspond to visible or ultraviolet photons. And so things on the order of 10 to the minus 19, maybe to 10 to the minus 18 joules, things of that sort, okay? Molecule will also be going from a rho vibrational state in the ground electronic state to a rho vibrational level in the excited electronic state, okay? So we're going to be changing lots of quantum numbers here. Some of that will show up, the vibrational part will show up fairly clearly in many cases. The rotational part, for the most part, will not be detectable in electronic spectra. And as we look at a spectrum in a moment, we'll talk about why that might be. In order to talk about electronic spectra, we need to consider something known as the Born-Oppenheimer approximation, which another expression of this is something I think I'll mention in a few minutes called the Franck-Condon principle. But the Born-Oppenheimer approximation basically, in really simple terms, says that electrons move a lot faster than nuclei, okay? So as we promote an electron from a lower energy molecular orbital to a higher energy orbital, the bond should get weaker. Right? Because we're moving an electron, usually we're moving an electron to an anti-bonding orbital from a bonding orbital. And so when that happens, it's definitely going to reduce the bond order. Therefore, the bond energy should go down. The bond should get weaker. The atoms should want to pull farther apart. Right? So the equilibrium bond length is going to, in pretty much all cases, be longer for the excited state than it would be for the ground state. All right. When this transition actually takes place, though, the electron changing orbitals, that will happen much faster than the nuclei can actually correct themselves, okay? So at the instant that the transition takes place, it's going to have to take place at some fixed bond distance, okay? Because I can't move the nuclei to get to that new equilibrium distance. That means that in pretty much all cases, a transition will go to an excited vibrational state in the excited electronic state. All right, we'll look at this right now, I guess, a little bit with some potential energy curves, okay? So this is, it says energy over here. So this is a potential energy diagram. Down here, my x-axis is distance going that way. That r, that distance, think of that as the bond length. That's the distance. If it's a diatomic molecule, that's just the distance between the two atoms, okay? Down here, this is my ground electronic state. This is my excited electronic state. Okay, and the excited electronic state is at a much higher potential energy, right? It's still a molecule, it's still bound together because there's still a minimum down here, right? Here, we've got drawn a wave function that might match the ground state vibrational wave function in that ground electronic state. Right? If we're in at room temperature, we expect at least most of the molecules to be in that ground vibrational state. So that's often the only one we really need to think about, okay? If I go to make my transition from this curve up to this curve, that's from the ground electronic state to the excited electronic state. So I'm promoting an electron to that new molecular orbital. When I do that, on this diagram, my transition needs to be represented by a vertical arrow. Okay, so I can't go from, if I say, well, this is the normal bond length in the ground state, that's the highest probability. I'm not going to be able to go from that bond length to this bond length, right? My vibrational levels are a little bit skewed up there in the top state, but that line that would very definitely be at an angle, right? Because the bond distance, the bond length at the normal equilibrium separation is going to be longer in the excited state. So instead of doing that angling arrow, I have to go vertically, which means that I'm going to land somewhere up here in a much higher vibrational state, right? That's the point at which this wave function and this wave function will actually have some significant amplitude, both of them, and that's what leads to that being the preferred transition. Okay. Now, once I've formed if I get up here in this state, this is going to pretty quickly drop itself back down, right? But that's just going to be the molecule emitting some IR photons to work its way down in energy before probably it eventually just comes back down from the ground, from the excited state altogether, right? If I turn the light source off, my molecules aren't going to want to stay up there in the excited electronic state because that electron's going to realize there's a place where it could go at lower energy, and it's eventually going to come back down there. So the overall process after the absorption takes place is complicated. Our absorption is going to show us that this could land here. If I drew more vibrational levels up here, I'd have more states that it could go to, right? So I'm going to have a transition from this from this state down here, the ground vibrational and electronic state. I'm going to be able to go to any of a bunch of electronic vibrational states in the excited state. Okay, this is what is known as, when we talk about this vertical transition idea, we usually refer to that as being the Franck-Condon principle. The same argument is in what is known as the Born-Oppenheimer approximation, the phrase I used on the previous slide. Okay, but that's what dictates what states we're going to be able to move between. It's not exactly a selection rule like the one we had, the ones we had in the IR spectrum case. All right, so let's look at what a real spectrum would look like. What I've got here is a representation of a spectrum for absorption of visible light by iodine gas, I2. I have this one because this is a sort of classic experiment in PCAM labs. I manage the PCAM lab that the chemistry majors take, and they do this experiment. So I happen to have a bunch of spectra around for it, and that's where I got this one. Okay, so if you look at this, you will see that much like our IR spectrum, we once again have quite a lot of peaks showing up, right? I've got wavelength this time as my x-axis because it seems that I like to keep us guessing for what's going to be on the x-axis of these things. This end is short wavelengths, which means this is high energy, right? Wavelength is increasing this way, and that means energy is increasing that way. It helps to kind of make sure that we're clued in on that, right? There are a bunch of peaks. If we could look at them more closely, you can kind of see in this region here that the peaks look like there's actually multiple peaks on top of one another in there, right? Out here, if I could zoom in on these look much more like they're individual separate peaks, okay? And then eventually out here on the high energy end, things really just come together, right? And that actually corresponds to the place where my vibrational levels in that upper electronic state are getting really close together because I'm very high up the vibrational ladder. Notice on the bottom down here, I've got a series of labels. V double prime, remember, that's the vibrational state, vibrational quantum number in the ground state for the transition. That's the initial vibrational quantum number. So most of my peaks say that I start in V equals 0 in the ground state because that's where most of the molecules should be, right? For that one, I get a lot of peaks. The one that we drew in there as the vertical arrow that hit the point where the wave function was very large in the top, that should be one of these tall ones somewhere around there, okay? These would be the peaks higher up, right? This is higher in energy. It says my energies get higher going this way. So that means in terms of here, let me go back for a second. In terms of this diagram, when the energy is higher, that means my transition is coming out further up on this potential, right? Because I need a longer arrow in this picture going up. That's what corresponds to a higher transition energy. And then you'll notice that in this case, I also have some peaks that are labeled as starting in V equals 1, and even some that are listed as starting in V equals 2. That's somewhat unusual. It happens in this case mainly because iodine happens to have a very low vibrational energy. Okay, the bond between two iodine atoms is not very strong. They're big atoms. It's a single bond between two large atoms, and so it turns out that the vibrational energy or the force constant for that bond is small, that means there actually are a decent number of molecules that are vibrationally excited even for a sample at room temperature like this one, okay? Iodine, by the way, is actually a solid at room temperature and pressure, but it's a solid with a fairly high vapor pressure. And so to take a spectrum like this, what we have in the lab is we have just a sealed cell, which has all the has been evacuated, and then it's got a little wafer of solid iodine in there, and it's sealed up, and then enough of the iodine evaporates that it generates the gas phase that is what the spectrum is looking at. If you actually have if you have a cell that's at least several centimeters long, and you look through it lengthwise, you can tell that the vapor has sort of a purplish tint, and that corresponds to this absorption that we're looking at here, where we're absorbing visible light. So it gives the gas a little bit of a color to it, okay? So I can see a lot of things in this. So these different sets of peaks, those are starting higher up, right? So if I came back here, if I were to start, instead of, it's getting a little messy on here, but if I started from a vibrational energy level that was, say, here, instead of down there in the bottom one, if I started up here and drew arrows going up, you could see my arrows would be shorter, right? Because I've essentially got a head start in getting to the top state. That's why these come in at successively longer wavelengths, showing that they're at higher energy, right? In principle, we're changing rotational quantum number as well. It's not usually possible to see the rotational lines in an electronic spectrum. The reason for that is because you'd have to have a very small uncertainty in your energy while the energy itself is big. What we might call delta E over E would have to be very, very small. Okay, it's very hard to get that sort of wavelength accuracy when your photon energy is very high. And so the shape of these peaks, if I were to zoom in on one of these here, say pick that one, and actually look at the shape of that envelope, that is related to the rotational states that are being changed as the transition takes place. The height of the peaks in this case is related primarily to how strong is that transition based on this overlap of wave functions between the ground vibrational state wave function and the vibrational wave function in the upper electronic state, okay? That overlap, meaning the extent to which there's amplitude of both of those wave functions at the same bond distance, that's what usually dictates the height of the peaks in the spectrum. And there is, once again, a lot of information we can get out of this because we can get information, we could get in the vibrational energy level separation, we can get information about the electronic states. If I wanted to put together a potential diagram, I think I have one for iodine coming up on the next slide, so maybe I'll just go to that. So this is a potential energy diagram in some gory detail. We're not going to talk about all the labels that are on there, but this is actually for the case of iodine molecule, right? And so it's got a third electronic state in there that we're going to ignore for the moment. But the transitions in that spectrum are like the ones drawn in the arrows there, right? And so there's basically no way to go from V double prime equals 0 down here to V prime equals 0 up there because there is no distance at which both of those wave functions can exist, right? This says that if this diagram is accurate, if I start here and I were to draw the strongest transition going up, it should probably be this one, which would be to a relatively high vibrational quantum number. I used to know this from doing this spectrum in the lab, but I haven't actually taught that experiment in quite a while. It's somewhere around V equals 27 or something like that, I think, if I'm remembering right, but don't quote me on that, where that one comes out to have the strongest peak, right? And then I get a lot of other peaks because this wave function, it doesn't exist only at that one distance, right? It's got some width to it here, and that means there's a range of distances over which I can get to the upper state, which is why I get so many peaks, right? The vibrational energy levels up here, just like our anharmonic model says, are getting closer and closer together. That's why the peaks get closer and closer together as we went to that high energy side of the spectrum, right? And so that should make sense to us from there, right? There's a lot of other stuff in here that is way more detailed than we need to get into. You can tell that the minimum in this curve, the equilibrium bond distance for the excited state, is in fact significantly longer than the equilibrium bond distance for the ground state, that's what would have to happen, right? Because in this case, we're moving, if we do the HOMO to LUMO transition in I2, you're definitely taking an electron from a bonding molecular orbital to an anti-bonding molecular orbital. So you're going from having a bond order of 1, you're going down to having a bond order of 1/2. And so you would expect the bond to be much weaker because of that. Right? Up here, incidentally, if my excited state were to dissociate, you'll notice that it comes out up here with one iodine atom in the ground state, what would be the S2p5 electron configuration you'd expect for a halogen, and then the other one is in some excited electronic state where one of those electrons is in a higher orbital, and so that's why it dissociates up here at a higher energy than this one would down there. Okay, so there's a really lot of information. The overall shape of this pair of potential curves can be pretty much entirely calculated out of information that is in that spectrum that we looked at a moment ago, right? And so there's just a lot of different information that can be gotten from a detailed spectrum like that. We're talking about model systems, and for electronic transitions, there isn't a good universal model. I've said that already, I think. For some electronic transitions, though, the particle in a box model works decently well. I talked about this when we launched into the particle discussion, right? The idea that there are places where we have, say, a series of conjugated double bonds, and that for those where I have delocalized pi electrons, the particle in a box model is at least a decent or qualitatively correct description. It's not great, but it is, I would say, remarkably good in matching what we see experimentally, considering the simplicity of the model. So let's take a look at a molecule that would have a string of these conjugated double bonds. This is an example of a molecule that is one of a series of what are known as cyanine dyes. Okay, that's a set of molecules whose structures are like this, where the number of carbon atoms in that central part of the molecule will vary from one to another. And so in this case, between the two nitrogen atoms, if I just look down that backbone, I've got 1, 2, 3, 4, 5 carbon atoms in there. I could go to 3, go to 7, go to 9, whatever, and I would still have a molecule whose structure would look very much like this one. Okay. Notice that my whole thing is an ion because I've got this positive charge on the nitrogen there. If I had the actual dye, it would just have that along with some anion, right? And that's how I would be able to dissolve to make a solution to use for dyeing if that was my intention. Notice that if I were to draw resonance structures for this, I could do one where I flip the double bonds, right? And if I did that, I'd have a double bond in that spot. I'd have a single bond here. I'd have a double bond, a single bond, a double bond, single bond. And when I did that, my plus charge would also hop down there, right? And my lone pair would be shifted to that end. And so that shows me where there are electrons that are actually spread out and roaming the length of that molecule. Okay, that says that I have a number of electrons that are going to be free to move down that central part of the molecule. And then I have the bonds to the methyl groups around the edges, right? These bonds aren't going anywhere. And so this is at least close to being a one-dimensional box, right? Where that length is the distance over which those pi electrons will be able to wander. Okay, and so that's our box. The electrons are the particles that are in there. One thing that's a little bit different is I've got several particles in my box this time, right? Because I've got a number of electrons in there. And so we'll have to confront that as we set out to try and calculate what we think should be a wavelength for a transition from this. So these are spectra for a series of these molecules. The molecules there have 3, 5, and 7 carbon atoms in the central part of the molecule. Okay, so the one that was in my slide before was the 5, which is fairly obviously the one in the middle. The 3 and the 7 are the others, and we will look at how those vary. We should remember, I guess, that 3 is going to be the smallest box and 7 is going to be the longest box. When we make the box bigger, we know that the energy levels get closer together. right? And so that means that the long wavelength on there should coincide with the long box. And so the peaks in there really are in order from 3 to 5 to 7 carbon atoms, I guess. One of these dyes that says over there produces a colorless solution. So it's not really a dye. It's just in the sequence because it's got the same homologous structure. And again, if we are in class, this is one of the sorts of things I often ask as a question using the clickers. And to answer that, you need to know a little bit about the visible light spectrum, I guess. And that is specifically that the wavelength over here, my 309 nanometers, that's into the ultraviolet. You're not likely to find a human who can actually see 300 nanometer light. Right, 400 nanometers is out towards the purple side of things, and that is about it for anything that people are going to be able to see, right? And so that 3 carbon one, the one labeled as dye 1 in the picture, would end up making a colorless solution because the light that it's absorbing is in the ultraviolet. That means it's not changing the fact that if I hold it up to white light, to visible light, all the visible wavelengths should pass through, meaning I would see the solution as being clear, okay? So that's just a little bit of an aside about visible light, I guess. So here are some bond lengths. And what we're going to do is we're going to use those bond lengths and that structure and what we know about the particle in a box to attempt to estimate what we think would be the wavelength for this transition, right? The slide that I just had there has the answer in it for what the wavelength really is. So we'll be able to do a comparison with that value once we do the calculation, okay? If I look down my chain, let's think about what's actually going on. Okay, so I've got in my my chain length, I've got one carbon nitrogen single bond, so I've got one of those. I've got one carbon nitrogen double bond. That's this one for the single bond, that one for the double bond, right? I've got 2 carbon-carbon double bonds, and I've got, that's 1 and 2 there, and I've got 1, 2 carbon-carbon single bonds. So that's my count of all the different bonds that I'm going to have in my chain, right? Then I'm going to have to figure out how many electrons are roaming in my box and how to deal with that. Okay, so I'm going to use these numbers to calculate the chain length. Okay, so maybe I'll just do that part right here, since I've got the numbers of bonds written up there. So I will want my chain length, which is going to be the length of my box, is going to equal 2 times 0.154, and all my lengths are in nanometers, so I'm not going to write out the nanometers, plus 2 times 0.134, plus 0.147 plus 0.127. And if I add all those numbers up, I have notes nearby that say I should get 0.850, and that's in nanometers. So that's going to be the length of my box in this case, all right? And I'll just carry that with me as I go to the next slide to figure out what's going on, okay? So this is my molecule again. We just calculated that L, the length of the box, is going to be 0.85 nanometers. So I'm going to write that down before we forget. All right, the next up is, remember our energy expression for the particle in a box, right? And so our energy expression says that En is equal to, let's say, N squared H squared over 8mL squared. That's the energy, right? I want to figure out what energy levels my transition is actually going to be between, right? And so to do that, the first thing I have to do is figure out how many electrons I'm working with, right? So I want to count the pi electrons. So I've got 3 pi bonds. So that's 6 electrons. And then I've also got a lone pair that's toggling back and forth, right? Because again, if I were to draw that other resonance structure, this lone pair of electrons is moving down to that end, and then the bonds that are in the three double bonds going along the midsection are also moving, right? So then I get the lone pair is two more electrons. So that says I've got a total of 8 electrons that are going in my box, right? And so I need 8 electrons altogether. My particle in a box energy levels are not degenerate, right? So they go and they get what? They get further apart as we go up, right? So if I were to draw those, that would be my n equals 1, 2, 3, 4 energy levels, right? Those are going to be what are going to function as my orbitals here. I'm putting electrons into them, and I'm putting 8 electrons into them. So I'm going to do what we always do when we put electrons in orbitals, and I'm going to just say I can put 2 electrons in each of my energy levels as long as they have opposite spins. So just like if I was drawing electron configuration, I'm going to do that. So this is n equals 1, 2, 3, and 4. So that says I'm filled up to n equals 4, okay? And that means my transition is going to be from n equals 4 to n equals 5. That's going to be the lowest energy transition, right? So I want to go from n equals 4 to n equals 5. I seem to struggle writing 4s with this pen. So that's the transition that I want to find, right? My delta E, if I go back to my energy equation here, right? The only thing that changes between the two cases is the n squared piece, right? So my delta E for this is going to be equal to 5 squared for the case that n equals 5, the high energy state, minus 4 squared for the lower state. And then all of that is going to be times the rest of the stuff that's there, right? Times, it's not h bar, it's h. I'm sorry. I did an h bar that I didn't need to do. So I've got h squared over 8 ml squared. My front piece there is equal to 25 minus 16, so that's 9. And so all of this is 9h squared over 8 ml squared. That's a square, really. Okay, so let's now put in, get that for an energy value, right? So I'm going to have that delta E from there is equal to 9 times Planck's constant, which is our familiar 6.6 to the minus 34th power joules and seconds. That's squared. Down here, I need an 8. I need their electrons, so I need the electron mass. Which is times 10 to the minus 31 in kilograms. Oh, that was really bad. And then I need L squared. L is up there in the corner, so that's going to be 0.85. And I want to work in SI units, so I'm going for meters. So I have to do times 10 to the minus 9. And that's squared. If I multiply all that out, I'm starting to run out of room here. I will get, according to my notes, 7.5 times 10 to the minus 19 joules. And then from there, I would do, I'll just come up here for a second, and I will say that I wanted to get lambda, the wavelength. Lambda is going to be equal to hc over delta E. And if I put in h is Planck's constant, c is the speed of light, I will tell you that if I put in the numbers for that, since I'm running out of room to write this, that I would get 2.65 times 10 to the minus 7 in meters. Which I could normally write as 265 nanometers. All right, so that's what my model predicts for this wavelength, right? The actual experimental wavelength for this, according to the slide that was up before, and the figure will be back in a second, was 409 nanometers, right? So our model does a sort of kind of job of matching that. It would give us the right sequence of wavelengths if we compared them. What does all that mean? It means that these electrons that are wandering the length of the box, in order to get the wavelength to be longer, that means the energy is smaller. That means my box would have to be a bit longer, right? And so there is actually some that suggests there's some spilling, if you want, of the electron density beyond the two nitrogen atoms, okay? And so the model's not perfect, but it does do at least a decent job of getting us there, okay? This one tells me what? It says that if I did that calculation for the three of them, I just did the 265 case, right, which is the one in the middle. This points out if I did that same calculation for the ones with 3 or 7 carbons, I would get the numbers here, 149 and 388 for that, meaning in all cases, we're underestimating the length of the box, right? And so I cut off my electron movement to be like it was in there. I also call the thing one-dimensional, right? And this has a little bit of shape to it, and so it's not totally one-dimensional. But if we let the box kind of spill out down to there more, something like that, we might get, well, we would get a somewhat better match to things, right? The textbook actually does a calculation where it calculates what the length of the box would be to match one of these wavelength numbers, okay? And so if you're interested, you could look at that calculation in the example in the book, which would show just how much longer the box would have to be in order to get this model to hit the wavelength that we see experimentally, okay? As you can see, this is not nearly as robust a modeling of the electronic spectrum as what we saw for the infrared cases. One more thing I guess I'll say is because the spectrum that we're looking at now for these dyes, those obviously look a lot different than the one I showed you for iodine. Just occurred to me that I might comment on that. The reason for that is that iodine spectrum was for iodine in the gas phase, right? And so those are isolated molecules, and each molecule is in a particular quantum state. These spectra would be for these dyes in solution, right? And so in the liquid phase, there's a lot of interaction between molecules going on, things like that, plus the dye itself is an ion. So there's clearly going to be a lot of interactions between the ions that are present in the solution. What that tends to do is it tends to take, and what we're seeing here is just a broad envelope of what in principle would be a whole bunch of peaks if we had resolution to see and separate those. Right, this will complete the current module, which is admittedly a short one. This brings us through, in terms of the textbook, to the end of chapter 4. Right, going forward, your next set of modules will deal with chapter 5, which involves statistical mechanics. So we're going to change gears a bit and talk about a lot more about probabilities and some mathematics associated with that, and a little bit about some thermodynamic properties and a somewhat peculiar way to be able to calculate values for that. We will still be drawing on our quantum mechanical models, so don't put chapter 4 away entirely. These ideas will be coming back as we go through chapter 5. Thanks.